Hello.
Yes. Is it working? Is it working? No, 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 no. Sorry? Works or not? Yeah. Sorry,
What does it say after?
evolution of here, time evolution of an angle. So I'll do my best, but yeah. Yeah. Tell me if you don't understand my ranting. I can absolutely agree. Is it working? Great. Then I think we are, yeah. Oh, couple of, yeah. And then we are done. And today we are on time. Great. Good. Good morning, everyone. First of all, an announcement. Thank you very much for the questions you asked in Moodle. I noticed that the solution of exercise 2 about the probabilities is not that clear. I will update it this afternoon and also answer to your questions. It will just be the two together. And if anything is still unclear, just write on Moodle, email, everything you want. Sorry for this inconvenience. Then today we are looking at time evolution, especially of states and operators. And the exercise sheet is really about it. And afterwards, we also spend a few words on order operator evolution, so to say, and in particular angle, because the exercise 3 is about it, but this will be quite short. So we start with time evolution. So one is time evolution. And as always, stop me if anything is unclear. So we start with the Schrödinger's equation. And by now, you probably also dream about it because we saw it already so many times. So a big problem of quantum mechanics is solving this equation because we have the state on the left and right side. And here we have a time derivative, and here we have an operator or matrix. So our goal is to find a time evolution operator such that we can characterize any state at time t as an operator times an initial state, t0. So the idea is we have an initial state, we time evolve it, and we have a final state. And this is the current state. And this state must solve this equation, of course, or because this is like the basic or like the equation of quantum mechanics. So now we have like special case. So for uniform dynamic, this you saw already in the lecture, we have the Hamiltonian is time independent. Okay? And in this case, therefore, it follows that our evolution operator only depends on the time interval. Yes? Okay, this is a question. So it tells you that the state of the system varies, but yeah, as a function of the time, varies as the Hamiltonian applies to it. Like, the idea is like how you can make a connection between the time derivative and this. Is that your question? Exactly. Yes. Yes. And a time derivative, you can. Oh, thank you. If you think in 1D, and you have this function, the steepness of the function is the time derivative. Okay. So this is exactly how the state changes. And in 1D, here we would have a constant, but the state is not 1D, so you can imagine it as a vector and vector representation. So it's like every component, how every component of the state varies. Not parallel. It can have a steepness error, like this would be allowed. Or yeah, yeah, it's a line. Yeah, exactly. Yeah, exactly. Yeah, 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 yeah. But I mean, imagine a Hamiltonian as a 1D. It's a bit, but yeah, this is absolutely the idea. So the Hamiltonian tells us how the system changes in time. Thank you for the question. So here we have exactly like, yeah, it doesn't matter if we are at time 0 or at time 10. If I wait 1 second, my state will change by this operator, which is only the this change, okay? Because the Hamiltonian is time independent. The change of the state is always kind of constant. So the state changes always in the same way. How, so to say, to connect with your question. And yeah, here we write it, yeah, if we write, and then notation for t0 equals 0, we write u of t minus 0, like u of t, okay? It's like if you see one variable, it means exactly that here we have at 0. Okay, or otherwise it's just, this is kind of a u of delta t, which we can write just a u of t. Because we can always choose t0 as 0. If, of course, you will look at the time, the state of the system at 10 seconds and 20, then you will always have to write from 10 to 20, and you have multiple times. Great. Then just a comment. I think this we will never see, but to just let you appreciate how this property satisfies our, simplifies our life. What if we have it time dependent? Well, u of t0 will be e to the minus e. Sorry, yeah, here I completely forgot to write that u of t0 in this case is equal to e to the minus I divided by h, h times the time interval. So here you see how important are exponentiation of matrices, because h is an operator. We can write it in matrix form. We multiply it by the time interval and by this constant. This is our time evolution operator. So for a uniform dynamics, if we know the Hamiltonian, we can, and an initial state, we can calculate the state at any time. Okay, so this is very powerful. of course, the problem is this exponentiating the matrix. Okay, we saw last week that it's actually, yeah, not that fun, but there are simpler cases and everything. Many times, actually, it's possible. In the exercise class, in real life, this is what, I don't know how many thousands or millions of physicists are up to, finding other ways to solve this, because exponentiating a matrix is very difficult. What's the case for time-dependent Hamiltonian? Here we have to integrate as the Hamiltonian varies in time between T0 and T. So this is an exponential. So first of all, we have to integrate this matrix, which is time dependent from T0 to T. And then once we have it, then we exponentiate it. Okay? I think this case we will never see in the lecture or in the exercise. It's just to make the difference. Of course, here is, as you can see, for here, for h from t h, so time independent, this integral reduces to this product. Yes? So the Hamiltonian is Hermitian, so yes, it's always diagonal. Yes, exactly. Yeah. Diagonalize it.
But this is not so hard.
Already, let's try to diagonalize on Wolfram alpha a 16 by 16 matrix. Yeah, but the problem is, like, for example, my research, I have a chain of 40. Actually, even 100, but the simpler one is like 40. And each here has a 4 dimension. So my Hilbert space is 4 to the 40. This matrix, you cannot diagonalize it anymore. Yeah, exactly. Even say, okay, it's sparse, but yes, yeah, that's the problem. This is the problem of, and actually this is like my toy model, just to see like this. If I go to real physics, then it's 120 at least. And we also have continuous Hilbert space. So there the matrix is even infinite. Great. So yeah, today we will just already see a tree-side, like a tree-side, and this will be already quite a mess. And fortunately, in the exercise is easier. So I will just show you an example so that afterwards you can only appreciate the example we will propose you. And so yeah, our plan is time-independent Hamiltonian. So we go back to 1 because it's what we are doing. If there are any other questions, stop me. Huh? We have from the lecture u of t is equal to e minus h divided by h bar at, and this is equal to k e to h a k t k, and where what are these numbers? AK are the eigenvalues of H, and K are the eigenstates. Okay. So this is exactly the idea. Here I wrote, sorry, this thing on over the sum. Is everything correct? But it's just, yeah, here we don't sum up. So, oh, this is way more elegant. So yeah, as we saw, diagonalize the matrix, and we know it's exponential. Great. So now we are going over a cook recept, which means cooking recipe for the non-German speaking. As a non-native, I love this word, of how to time evolve a state, which is what you will have to do in the exercise sheet. Time evolution, the evolution of a system with time-independent Hamiltonian. And it will always, so it will work like this. Tell the general case, so the general procedure. Then we have an example, and we calculate for this example. And then we have the simpler case, which is a bit more in the direction you will do in the exercise sheets, in which maybe you have less terms, or you don't have to calculate as much as we do in this example. So we have our example. So we have a basis which I call 0, 1, and 2. And okay, we write these vectors in the vector representation. And I have my Hamiltonian, which I just tell you, this is H 0, 0 plus 2b 1, 1 plus b 1, 2 plus b star 1 plus 2b 2, 2, which in matrix form, I can write it here as 2b, b, g, b. These other elements are 0. But yeah, many times we just leave away the elements which are 0 because many matrices are sparse. Okay. And so yeah, and I have an initial state. This is given, and this is 1/2 of -0 plus 2, 1 plus. Could I write here 1/4 instead of 1/2? Yes, no, why? Yeah.
No, because it's not normalized.
Perfect. Okay. This is a normalization constant. In case, maybe it can be that sometimes they give a state or initial state superposition. Check that the initial state is normalized. But I think, yeah, in the exercise sheet, everything is normalized. Yes.
Or is it all like some specific structure? For example, why do we not have the 2A01?
Yeah. This is anything. This is given. Yeah. Absolutely. Yeah. And it's possible. I just picked up one. We can write also only 0. Yeah. The initial state, this is completely arbitrary. The Hamiltonian, this is also absolutely just random thing. I picked up one which is actually diagonal, like the diagonalization is not too difficult, but as you can see, it's already a mess, this one. So if you think a 3 by 3 with all of the elements, then no chance anymore. Yes? So the Hamiltonian is Hermitian because of a properties. If you start from the Schrödinger's equation, you figure out that the property of the Hamiltonian is that it's Hermitian. Yeah, you did it in the lecture, if I don't remember. It's in the lecture notes if this interests you. Yeah, great. So now we go for our cooking recipe. And the first, well, sorry, I'll just pick 2 colors. That's great. So the first is diagonalize the Hamiltonian. So we have, in general, I mean, there are different ways, but I would say write H in matrix form. And then I would say, because we are not in linear 1 or linear algebra anymore, put it in Wolfram Alpha, Python, Julia, or any programming languages to calculate the diagonalization. Because, yeah, of course, maybe in the exercise, in the exam, you don't have a computer, but you won't get a difficult Hamiltonian because we don't want you to diagonalize a 5 by 5 matrix. That's not the point of quantum mechanics. No one diagonalizes a matrix by hand. The one I wrote there, I put it on my computer and it returned my eigenstate and eigenvalues, and that's all. Great. What's the example? So we have H is written there, and I can list you, I just tell you the result, eigenvectors and eigenvalue. So the first eigenvector is exactly our 0, the basis state, and the eigenvalue is A. The second is, and this is the superposition of 1 plus 2. And we write it as a 1 tilde. I just define it like that. You will see later that it makes all of our calculation easier. And the eigenvalue is 3b. And here we have 0, 1, minus 1. And then here is the superposition, but with a minus. And this I call it 2 tilde. And the eigenvalue is b. So yeah, this step, just take it like that. What's the simpler case? We write, for example, H proportional to, okay, this is like what we saw last week. Okay, this means A Sx. An operator, which is, for example, the Sx operator or the Sz operator. And these are operators with known eigenvectors and eigenvalues. This is something you saw in the lecture, or that Sx0, plus is 1/2 minus, if I remember correctly. Yeah, no, is what I have. Yeah, plus and Sz of 0 is 0, 1/2, 0. Probably there is a constant I, something like this. The idea is just, we know the eigenvalues, we can diagonalize it straightforwardly. Yes? Yeah, ooh, so you didn't see in the lecture, I read again, sorry, I don't. SZ is I divided by 2 Z matrix. Or there is a constant in before, and Sx is also, yeah, let's write it proportional. This is very correct. So these are the eigenvalues of the X and Z matrix. Okay, and these you saw already, these I'm sure. Or that, yeah, the 0 is an eigenstate of the Z matrix, and the plus is an eigenstate. The 0, 1 are eigenstate of the Z matrix, and plus and minus are eigenstates of the X matrix. So if you put a constant in front, eigenvectors don't change at all. So yeah, if we know this already, we can just diagonalize it straight away. But in our case, this is not our case. So we have to move further, or actually even in the simpler case, we have to move further. What's 2 is right the initial state in the basis of the Hamiltonian eigenvalues. What does it mean? Here we found some case. Okay, so this is like our set K and our set of eigenvalues K, which we wrote exactly here. Okay, eigenvalues and eigenstate. So find, this means we had, so in general, we have that psi of 0 is a sum of, is a decomposition of some basis states n, which are given. And in my case, in the example, my states n are exactly 0, 1, and 2. Okay, I wrote these as a function of t. And this means we have to write, so find hk so that psi of 0 is equal sum over k of hk. So I have to write it as a basis of the in the basis of the eigenvectors. And here we can do it with a basis transformation. Or a linear system with at the end is exactly the same linear system of equation. And now we will see straight away what I mean with this, because in my example, I had psi 0 in these cases, or like this. Here in vector form, I write it as -1 to 1. But now I want to write it as some h time my first eigenstate. So this will be exactly alpha, sorry, 1, 0, 0, plus some beta, the second eigenstate, plus some gamma, the third eigenstate. So this will be alpha in my new basis. Tilde plus 2 tilde. And here I can also put a tilde so that we see that so this is 0, which is equal. I just take the same state. Is this step clear? Yes?
I just want to ask, because in the vectors we have right now, all the vectors are normalized.
Yeah.
Would we then basically need to also take the normalized eigenvectors?
Yes, exactly. Yeah. And normalize. Very good question. Actually, I wanted just to do it right now, but yeah, good, very good. Yeah. I will show you now here the result is actually I wrote it somewhere, which is so yeah, here we have psi 0 is equal to minus 0 plus 3/2 1, this is a tilde, plus 1/2 2. And these are the coefficients I found, but then I have to normalize. And this gives me, so here I would have a 1 plus 9/4 plus 1/4, which is 14/4, which is 7. So here, if I did everything correct, here I put a normalization 1 square root of 1 over the norm, which will be 1 over 7/2, which is 1/7. So yeah, this is right the initial state in the basis of the Hamiltonian eigenvalues. That's what we did. And yeah, simpler case. So which is usually what you have in the exercise is usually a simple system of equation or something, you know. So it can be that the initial state is very clearly already the superposition of two eigenvectors, something like this. But this is a step which we can still do. Are there any questions? Okay, then let's move to point 3. Let's bring it here. So. Three is time evolve state. So now we have diagonalized our Hamiltonian. We have our initial state in this eigenvector basis. So what's the general case? We have that psi of t is equal to the sum over k of e to the minus e divided by h bar a k t k k, and this is my time evolution operators times my phi of 0. And now, why did I do this? Because now I can write this in the basis. So if it's not clear, I will relook at it again. HKT, K, K, and I write my state in the eigenvector basis. So here I found some HK, which now I call K prime, of K prime. Why is this very cool? Because now I write it as K prime e to the minus a divided by a bar a k t of K prime, And here I have a HK prime. And how does it simplify now? Anyone see what's the, yes?
Basically, every multiplication where the K and K prime do not match up are going to be 0 because they're
Exactly.
all
Yeah, this is.
one wherever else where the K doesn't match up, so we can basically simplify this as the sum of K.
Perfect. Yeah, this is a K prime because the eigenvectors is an orthonormal basis. Yes? Okay, yeah, so here these are normalized. Yeah, so eigenvectors normalized.
Zero, one, one is not equal to one's variables. So this is the normalization factor on the left, right? You have to normalize that first.
Here, this is. Yeah, thank you. Yeah, very good point. Yeah, yeah. So once you find the eigenvectors, this, yeah, it's like 2 steps in 2, but usually you find the eigenvectors, then you define your new basis, and then you normalize it. But yeah, perfect. If you just find the eigenvectors and normalize them straight away. Very good point. Thank you. So here, these reduce to sum over k to e to the minus e a k t h k k. And of course, these you don't have to do it. Like you can straightforwardly say, I have this result. I have my hk because I know the eigenvalues. I have my alpha k because I calculated them here. I input it. This, it's just kind of given. We show them now. So now we go to the example. So I have C of t is equal to square root over 2/7 of minus a minus e divided by h a t of 0 plus 3/2 e to the minus e divided by h 3bt of 1. Oh, here, sorry, I put a bit too much space, but yeah. H to the minus e divided by h bt of, and these are the tilde of 2 tilde. Yes?
Is there a reason why the divided by h is missing?
Yeah, that's very great. Thank you. Yeah. H bar, I'll write it like this. Yeah, H bar is always there. Then it can be, in many cases, we put it equal 1. But I think it's great just to keep it. Yeah. So now we have finally the time evolution of our state. What's the fact? Here, this is not the basis we started with. Okay, this is the eigenvector basis, which in this case is a superposition of the two. In some other cases, is even more complicated. And yeah, so what is a simple case is simple. I would say that this is not so complicated. This is, of course, if you have an easy phi 0, then this will also be easier. So the simpler case just follows from what you did before. Great. Then I have to find my sheet of paper and I can continue. We are here. Yes. Then we have 4. Is write C of t in the initial, so to say, initial basis, which is the one we wrote as n before. So not the eigenvectors basis of the Hamiltonian. And so in general, you have C of t or k from a k of t of k, and then you do basis transformation which means, so you write that k is a sum over some, which letter can I use? Rho, no, rho is very bad, and let's write a h tilde k n of t. Sorry, this is not h tilde n of n. So I input this, and then I will get sum over some n of alpha n of t. N. Is this clear? This is like reputting these 0 tilde, 1 tilde, 2 tilde here, so that I can then write a sum over the 0, 1, and 2 states, which I know are states I know. And in the example, I write here, as I now have to do here. If I put C of t, this will be 2 over square root of t. So the 0 tilde doesn't change. 0. And then for the 1 tilde, I will have a superposition of 1 plus 2 times 1 over square root of 2. And 2 tilde, I will have here 1 minus 2 with the normalization factor. Is this clear? So it's really inputting here, and now I will write the results, because it's not that interesting to do everything separately. I just group every prefactor of the different basis states. 1. Okay, yeah, this is everything, the prefactor for 1. And this is then 2 e minus e divided by h3b t minus, and then this is 2. Oh, here, I don't need this parenthesis. Now, at this point, we have some coefficients which are a bit maybe difficult or very tedious to write. Sure, here I need, of course, a parenthesis. What do I do now? I write this row 0. This is my row 1. And this is my row 2. So in an exam, I don't know how you're used to work or like this. You're absolutely, if you write explicitly the form of a coefficient, and you know that you will use it afterwards, then just simplify it, tell this is my row 0, this is my row 1, this is my row 2. Except if we really say find explicit the probability. Usually in the example we see these are easier numbers, so you can just keep on writing with these numbers. But now I don't want to spend the rest of the lesson writing these again, so we will just code like this. So today I know when the real break is. I would say we can do 10 minutes break and we continue afterwards. And yeah, of course, I'm here. Yeah, I'm here for any question. That's very possible, yes. Sure, thank you. Yeah.
I was just interested because you talked about this example before where you have this 4 times 40 in practice. Then how do you actually do any kind of calculations in quantum physics? Because as much as I know.
That's the problem. So what we're looking at now, you do it in 1% of the cases because it's impossible to do any possible thing. There are a lot of different ways of handling it.
Do you work with approximations or do you
exactly? So yeah, the keyword is approximations, and the main idea would be diagonalize Hamiltonians, but this is actually so complicated that at the end you do everything else except of diagonalizing Hamiltonian.
Okay.
You're a computer science student? Yep. Okay, so maybe you're interested. One thing I work in is like reducing these numbers of.
So you're trying to reduce dimensionality.
Exactly, yeah. So what we do is like I have so my different states, something like this, and then so like this many, okay. And these, if we have n state, sorry, maybe I get a bit too excited, but I think this can be interesting for you as well. And each of them, okay, that's great. Each of them is a d dimension, and we have a chain of n. So this would be a d to the n Hilbert space, okay? So what we do is we take, okay, let's take this versus this, so like kind of this matrix. And then we do an SVD. It's called this, you know, singular value decomposition. Okay.
Yeah, my last semester, my teacher.
Okay, yeah. And then I get a matrix. So here I get a matrix, and then a diagonal matrix, and then another matrix. Okay, this is SVD. And then we see the idea is, okay, the Hilbert space is huge, but actually our states occupy only a small portion of this Hilbert space.
Okay, so you basically reduce dimensionality by basically just cutting off the
exactly. So
the singular values are so small that it doesn't make a change.
That's exactly. I have here, and then I see these, they decrease exponentially because of some property of the physical system. So I just cut here.
So you're basically doing a matrix approximation.
Exactly. Yeah. This is
Funny to see these things from non-CSE popping up in quantum physics.
First, This is tensor networks. I don't know. They come.
Tensor networks I haven't heard, but
you see, okay, there are also other ways, but one of these tensor network means we reduce these numbers of the matrix elements. basically.
Are you doing this? Are you doing this kind of incrementally? So basically, you assume that you have this. You basically this kind. You assume you already have a kind of thing, and then you just reduce it, like in dynamic programming, something.
Yes,
like
exactly. Yeah, yeah. We do it one afterwards.
Very interesting.
Then there are other ways which are completely different. There is, we know also some properties of equation, and then, for example, you know about maybe the time evolution. So you take at the end only the operators. So you don't have any matrix representation at all, but you see either more like the, what's the name of the, like the qualitative behavior of the system.
Trying to reduce the number of operations by seeing, okay, you have many operators,
and
then you try to kind of put it together into one big
you saw like these A or this is like some exactly
basically simplify it
exactly
into no operations, so that you already know from all of these operations you have these.
And then here you have an age like this, and then these can be seen as an operator C. So this is also an exercise you see this week. So here you see that the dt of A can be the expectation value of another operator. And then maybe we put here E, C, and then we see that and we see H of T is equal A. So this part, dt, dH not dt is equal to 0. Okay, exactly. And then if we put in C, maybe we find another operator B. So at the end, we have a system of equations. And we don't care about the Hamiltonian representation anymore, because if we can exactly, we can say, okay,
because these things are easier to solve.
Exactly. Yeah. Then there are because actually, my research is many different methods. I'm most focusing on these up to now, but then we have another way is like if we have a system which is a couple of sides. And then this is very important, and then it's weakly coupled to others. Then we can start diagonalizing it, and then kind of slowly introduce the rest, which we care less about.
I see. So you start with the main idea.
Exactly, and this is a couple of something. Then we use this. So this exactly what we saw before. Yes. Then there is, so these kind of equations, there are other equations which you can relate between operators, because at the end we don't, or in my case, we don't want exactly to know the system, we know what. And then another huge thing is, this is quantum mechanics. So we have this superposition, and simulating it classically is a mess. If we put them in a quantum computer, which behaves as our system, then we are fine, because our qubit for nature have the properties we want our system to have. And this is also why there is this very famous publication of Feynman, which is like simulating quantum mechanics with quantum computers. And that's where it started a little bit. And for example, IBM already has some qubits, and also we can access it and play a little bit around.
Very fascinating, very fascinating.
Great, thank you. I'm happy that someone gets also fascinated, because this is my my work.
I'm doing this class actually also kind of to get introduced a little bit more into the nitty-gritty. Because it is one of the two paths I might choose to go in.
That's very great.
Right now going to cybersecurity.
Yeah, okay, I see. But there is also quantum cyber security. Quantum cryptography or something very,
But generally, I find it very interesting.
Cool. Very great.
Thanks for the introduction.
Yeah, thank you for asking.
I have a question. Very simple in your algebra.
Yeah.
You always write it right next to it, diagonalize them something like this, right?
Yeah.
Why? I mean, at this point, I've accepted I can do it. but why can I do it in linear algebra? Because we're moving algebra.
Okay, in
this
algebra, yeah,
have
of course, yeah,
I don't know.
yeah,
So these are my eigenvectors,
yeah,
eigenvalues.
yeah,
diagonalized.
absolutely,
I don't know what
great,
this is.
yeah.
These are
These are, yeah, okay. The fact is that this is every matrix with some specific basis.
Yes.
Okay, so if you choose the basis of eigenvalues, then you have exactly this. And these would be if you, M is a sum over Mn of alpha Mn Mn. Okay.
So this is the basis.
Exactly. And if I apply P to the M, then I have my states. These are my K. Oh no, just too much. This doesn't matter. But the idea is we apply a basis transformation. And if I write M as a sum over K,
What's K? What's M? What's B?
so these are the eigenvectors of M.
So what is this? This is just the
So
matrix.
this, okay, I have a basis.
Just the basis.
And I write the matrix as a, exactly. Yeah. Now I want to write the matrix as a diagonal matrix in another basis. So how do I do it? I diagonalize it, and then I have this V matrix. Here you can see that if you multiply by P minus 1, then I have that M P minus 1 equal PV. And then if I apply P, then I have, yeah, exactly, sir. Then I have P minus 1 MP is equal V.
Okay.
So I represent this matrix in another basis, and here this matrix is diagonal.
Okay.
This is the exactly the in the basis of the eigenstates, and that's why I can write this like this. I apply a basis transformation.
Oh, okay. Okay, so, oh, I think I see. So we, in the end, we write down V, which is because every matrix has this diagonal, it's just like diagonal.
Yeah, exactly.
And then
what we can see maybe like here, or this is exactly this step. These I had my eigenvectors, or like there, my matrix H is not diagonal in the starting point, but if I write it in the basis of 0 tilde, 1 tilde, 2 tilde, it is. And how are these 0 tilde are exactly these, which would be, this is, it's kind of applying P to 1 is equal 1 tilde.
So we okay. So this is P. Okay. So
this is PM is equal K. This is like P1 is equal 1 tilde.
Okay, that holds Y again.
Exactly. Yeah.
Why else does that hold again? Does that just hold in general?
Yes. Yeah.
Okay, so
yeah. If I calculate this matrix and I apply it to these basis states, then this is exactly an eigenstate. These are per property of linear algebra or definition. Either you see it.
we give us linear algebra first semester.
Yeah, this was not my first love lesson. Like this. Yeah, you can come later if it's still unclear. Great. Let's continue here. So yes. Right, then we are here. And actually, I didn't mention before the break, but it's a very good step because now, so the time evolution of the time evolution is known. So we reached a big milestone, or we have our formula of the state evolving in time. Now, yeah, and then in the simpler case, this is, yeah, it's everything simpler because of previous steps. So now we have a state, which is actually fine, but it's not the end of our story because we want to do more. For example, we want to know the overlap with the initial state or also any state. So what we calculate in general we will have our phi of t inner product with the initial state, and here we will have as a sum over n prime of e n prime dec of t n prime a n n, and this will be then the sum over n because of the properties we saw before. This is as a function of t, a n of n of, yeah, sorry, this is all. So now you see, for example, why is it important to go back in the initial basis? Everything we know usually is in the basis we defined at the beginning. If we stick on the one of the eigenvectors, it can become a mess. And yeah, what's in the example? Actually, I always use the color, so let's go back with the color. I have phi 0 equal 1/2 of minus 0 plus 2, 1 plus 2. So I do this operation with this here. And why did I simplify defining this coefficient? Because now I don't write all of the story anymore. I write it now as square root of 2/7 of 1/√2, which is the pre-coefficient of rho 0 dagger minus, because I multiply it by minus. So it's like the sum over this coefficient corresponding to the same basis state. And then I will have plus 2 rho 1 complex conjugate, and then plus rho 2 conjugate. Is this clear? Tell me if not. So yeah, here then I can of course like this. So this will become 1/√7. Yes. Here, yeah. So we saw in the general case, I want to make a superposition of the two, and with the properties of an orthonormal basis, I see that this is the sum over the coefficient of this times this corresponding to the same state. You see, this is an n and this is an n. So I start with my first state. So here I put the normalization factor so that I only have to see this coefficient. Okay, this is like only putting. Then I start in my first state, so n equals 0. Here I have a -1, and here I have a row 0. Exactly, yeah. So I multiply these two. Here I have a 2, here I have a row 1. Okay. So sorry, this is equal, and then this is equal like this. Equal is better. Like, oh, I don't know. Or I can write like this, and then no. Yeah, absolutely. You're right. Absolutely. Like this. Then it's correct. Thank you. Yeah. And great. Simpler case, it doesn't exist. Or yeah, it's like, again, here you have a few terms in a simple case. This is also only 3 states. If you have 10 already, you have to work a little bit more, but yeah, nothing to worry about. So now we move. Yeah.
What is the star complex conjugate?
Yeah, complex conjugate. Yeah, this is the notation Lidia used in the whole lecture. So A plus EB star is equal A minus EB. Okay, I'm pretty sure that it's used from the very first lecture. If you write it with a bar, because you're used to, we understand absolutely. Good. Then we can move to the next step. So we are 6 time evolution of observables, which means basically like excitation values. Yeah.
What's the meaning behind this overlap?
Yeah, so it's kind to see how much did it change, for example. If it's 1, then it means it didn't evolve or it came back. If it's 0, then it's like it's completely orthogonal. Yeah, this is meaning. It's what you can also see is you can also overlap it with a basis state or a state you know, and you want to see how similar is to the state you're looking to. That's why I wrote overlap with the initial state or any state. In the example, we put it the initial. Is it clear? Yes. So the 1 is as a function of t. You see here, there I wrote, in the general case, my state as a function of t. Here we could write of 0, but usually the fact is that usually you never do it, and that's why. So here could be alpha n of 0. but you usually never write it like that. That's why I put it. Yeah. So don't be confused if you see a alpha n of t and then, or yeah, something like this. Thank you. Great. Then, so now we have a state, but usually we don't look at the state, or in many cases we look at, I don't know, the energy or the position or an operator. So in the general case, and this comes from exercise 1B of sheet 3. And this is some new code last week. H for psi, H psi plus C dH now dt. And here, so here C is equal, so at time t. What are we doing here? In many cases, okay, so here we can write very often many cases we have that the observable is time independent itself. So the this term is 0. Okay, but this is really the general form of the equation. We come back to our example. And I choose operator, which is written like this. It's of course an example, any other can be chosen. So how can I write, and the question is, yeah. So we have to calculate the commutators, the commutator of the two. So what do I do? H times the Hamiltonian, and this will be 0, 2 times my Hamiltonian we defined before. Now you see Dirac representation is very convenient because you can, it's an orthonormal basis, so we can simplify everything which is doesn't have a 2 as a cat, and we will end up, if I did everything correct, as 0, 1 plus 2 beta 0, 2. Then we calculate H times A, and this will be an alpha 0, 2, because the only term with a 0 on the bra here in the H is this, so we multiply it by here. And then we multiply the H naught dt, which is 0, okay, because I don't have any time variable, any time dependence directly. What does it follow? That the time derivative of the expectation value of A is equal 1 over HA prime of C of T. And then I input my result here. So B dagger 0, 1 plus 2B 0, 2 plus A 0, 2 C of T. And okay, here I can write it like already. This I call it row 0, 0 plus row 1, 1 plus row 2, 2 divided by times, let's put it like here, times square root of 2 over 7, which was the normalization constant. So what do? I multiply these terms times this, and then multiply this result by this guy, which of course this transpose. And I get 1 over IH of, let's put it, a step more, deca 0. And here I also have to put 2 over 7 plus rho 1 deca 1 plus rho 2 deca 2. And then I multiply it with B star rho 1 0 plus 2B rho 2 2 minus A rho 2 0, rho 2. Here is a 0 and there is a 0, 0, 0. And this will give me 1 over H rho 0 deca rho 1 plus rho 0 deca rho 2 of 2B minus A. This is multiplication. I went a bit quick because it's not the point of our lecture. Why did I show you this example? So that you will appreciate the example you will see in the lecture and in the exercise sheet. In the simple case, we will see just right away. So the simple case, or I can write it, simple case. There are two possibilities. So one, way less terms. So we don't have to calculate all of these. And remember that this is also even easier because we defined this rho 1, well, actually it's a delta, sorry, I'm very bad with Greek letters. So we define these deltas to simplify our life, but even with this simplification, we have to do a lot of multiplications and sums and so on. Great. Then, what's the simpler case two? No. Yes. So here you have a square root. So this is phi of here. And you have a square root over 2 over 3. And here you also have a square root 2 over 7 of something. Exactly, yes. Okay, so wait, I'll just take colors. So these here, now, so like this will be square root of 2/7 of these. And then I have another here, this is square root of 2/7 of rho 0, 0, delta 1, 1 plus delta 2, 2. So let's write it like here, like this. Here I put square root 2/7. And this is exactly this. And here I put square root of 2/7. And then here I have to write it like this. Okay, so here we write. So this is our age. Let's put like here. Okay, and this is then my phi t. Yeah. And let's put like this as well. So this is my here kind of, and here. Is that clear? Okay. Yeah, this is very possible. Here, yeah, thank you very much. Yeah, 1b star. This is correct, and I actually had it. Yeah, thank you. So now we have even the where am I? Here, 1, 2, 3. I lost my sheet. Here, the less so simple case 2. And this is like, so the idea is that commutator A is this, you know. And this is, of course, also, you can define it as an operator. Because if you imagine this as matrices, the result is a matrix. So, and so in the simple case with the known. And also maybe the age, dt divided by derivative t is equal to 0. So a time independent operator. What does it mean from the equation before? We have that the time derivative is equal as C of t, C of t, which we define it exactly as the expectation of value of t as a function of t. Then maybe we have that CH is equal another operator B. This means that the time derivative of the expectation value of C will be B. And I think we write it like here, like this. Yeah. So what does it mean? We get a set of coupled differential equations. Okay, so in this case, now we have A, B, C, and 2, but in some cases you get as many equations as observables or as unknowns. This means you can solve ideally. So ideally is solve the system. And this is, I think, exercise 1B, sheet 4. If I remember correctly, but I think it's correct. Otherwise, you will understand straight away by looking at the exercise sheet, which exercise I meant. And this is a very powerful tool because this means that if I have these, I just don't have to do all of 1 to 6 we showed before. I don't have to calculate the eigenstate, the eigenvalues, everything. I have to calculate the commutator. If it's some matrices we know, that we solve the system and we have the solution. Of course, only for the time for the expectation value of some operators. We didn't solve the whole system. This tells you how does the expectation value change. If we solve it, then we know how does the expectation value evolve in time, but we don't know how the system evolves in time. But in most of the cases, it's actually more than enough. Great. Any question? Good. So this is actually all about the qutrit chapter. Of course, you can also do, there are many variations. The idea is, okay, we want to calculate the time evolution of our state. We have our Hamiltonian and the initial state. So we diagonalize it, and then everything starts to happen because you have a lot of terms. It's difficult. It's very easy to forget something. But in the exercise sheet, as said, is actually easier than what I showed here. But I hope that you get convinced that quantum mechanics problem would be actually only about diagonalize the system, but it's a mess in general. So now I have here, we go to 2. So now qutrit chapter is closed. Any question, you can come afterwards. We move to uniformity. So. And yeah, here is like other parameter evolution. So the idea is, okay, for time, we saw that if the Hamiltonian is in time independent, then it's actually, yeah, the evolution of operator only depends on the difference between the two. Okay, so the evolution operator at any time is equivalent. And so we can say that change is independent if we are at t equals 0, 1, and so on. Now we can ask ourselves also, why time So we looked everything at the evolution. If we start at 0, what's after 10 seconds? What's after 1 minute? But we could also look if the system is here, how is the system here? How did it evolve? So here the question is like that time is an external parameter and absolute for quantum mechanics. So this is our parameter, which you say we know what it is, and there is no question what time evolution means. As you probably know, or maybe some of you saw in high school or in some physics lecture, for example, space is something which is not absolute. In our real life, this is 1 meter, and it will be for you, and for everyone. But according to relativity theory, if you travel at a high velocity, this is not 1 meter anymore. This is maybe half or 20 centimeters or something similar. For time, this is also something different in time relativity, but also there, maybe you heard about the twin paradox. If someone travels to space and then come back, is younger than the other twin who stayed on Earth. But quantum mechanics tells time is absolute. Then, actually, Lidia would probably tell me that currently some group are also investigating this, and time is not a parameter anymore. So, but for this lecture it is. Or if you're interested, go talk to her. Or I don't know, you are also in that project? I have no idea about this. I only know Victor, who is working on quantum clocks, and then yeah, that's all. So for us, time is time, as you know, intuition and everything nice. Now. Yeah. Now we will see at another example where instead of time, we look at angles. And we have a state in this block sphere, and this state can just rotate. So we have our block sphere. Like this. I do my best, but I'm terrible at drawing. And here is the z-axis, and so we have that this is the 0 state, and this is the 1 state. And this is exercise 3, sheet 4. So what do we look at? The rotation around the z-axis. Of angle theta. And as you probably know, so a rotation for us, if we say around the z-axis of angle theta, we always look at counterclockwise. So this is the geometry, or I don't know, direction. So if we have a state here and we rotate it, then it will come here, and this is exactly theta. And let's say, so this is my sphere, oh, this is, but not in the sphere, which is bad, because of course our state have to be normalized. So this is C of 0, let's call it like this. And then I rotate it by theta, and I get here of theta. So I have my rotation operator. And psi of theta is equal to some, yeah, let's call it theta, no, Rz of theta, let's call it this theta 0, from theta 0 of psi of theta 0. So I have an initial state, which I call psi of theta 0, and then I rotate it by angle theta. And because as you probably imagine, two rotations will be independent of the space. Yes? Here, this is psi of theta, sorry. Yeah. So if you imagine, if I have a plane and I rotate by 45 degrees, this is independent if I'm here or here or here. This rotation is always like 45 degrees. It's independent on what my initial state is. So this is exactly uniformity. Rz of theta 0 is equal Rz of theta minus theta 0. For the evolution operator, we had this if we evolve the state for a time interval which is t, it doesn't matter if we are at 0 or at 10. Therefore, we have this u of t, t0 is equal u of psi minus t0. Here exactly, it doesn't matter at which angle I am. What only matters is difference. So we put theta 0 equals 0 most of the time, and then we call it Rz of theta. And what does it mean? That the rotation of two consecutive rotations are equivalent of a big rotation with the angle, which is the sum of the two. If you imagine like this, I start here, and then I do theta 1, and then theta 2. So these would be this and this, okay? Here actually, if I would be very correct, is like, so this is 1 and this is 2. And 2. And these would be theta 1 plus theta 2. Is that clear? So this is the uniformity condition, or it follows from the uniformity condition. And as a very last comment, what are generators? It's a term you see in the exercise. So the Schrödinger equation you have that EH dt psi of t is equal h psi of t, with h is the Hamiltonian. And for another parameter, that's why I called it other parameter evolution. The idea is exactly the same. I should find an equation. I call this parameter alpha. The alpha of psi of alpha equals some h psi of alpha. And this means, so yeah, in the exercise, alpha is our angle theta. And the question is, so the generators are this age. The question is, what is my age? Okay, so this is exactly the exercise. It's a bit guided, so you do some sub-exercise before, but I think this is most like the new concept you see, which we didn't cover before, and that's why I spent 2 minutes. If you're stuck, then you can write an email or write on Moodle. Otherwise, I'm done. Thank you very much for the questions, and yeah, wish you fun with the lecture, and I'm still here for if you have any doubts. See you next week or the after next week. I know you don't have to.